this episode, we focus on Puppet as a way to understand how modern Linux environments keep many systems consistent without relying on one person's memory or a pile of one-off fixes. Even if you never become a full-time automation engineer, the CompTIA Linux Plus exam expects you to recognize why configuration management tools exist and how they describe system state in a repeatable, auditable way. Puppet shows up in that conversation because it represents a mature, widely referenced approach to enforcing desired state across fleets of machines, including servers that live on premises, in virtualized environments, or in cloud platforms. What matters for your learning is not memorizing a command sequence, but being able to explain the concepts Puppet uses to define intent, apply that intent safely, and prove that managed nodes are actually talking to a trusted management system. By the end, you should be comfortable with the exam vocabulary around classes, modules, facts, certificates, and the difference between agent-based and agentless management models, because those concepts are the real target of most exam questions. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Before digging into Puppet's internal vocabulary, it helps to frame the broader problem it solves, which is that Linux systems naturally drift when humans administer them manually over time. A server might start with a baseline configuration, but then patches, emergency changes, troubleshooting edits, and quick, just this once adjustments slowly reshape it into something unique. That uniqueness is dangerous because it makes failures harder to reproduce, it makes security auditing less reliable, and it makes recovery slower when a server must be rebuilt quickly after compromise or outage. Configuration management, CM, is the general idea of treating system configuration as something that should be defined, enforced, and measured rather than improvised repeatedly. Puppet is one way to implement CM by expressing the desired state in a formal language and then repeatedly applying it so the system converges toward that state. The exam cares about this because drift creates security gaps, and consistent configuration is one of the most practical defenses against both accidental misconfiguration and opportunistic attack. When you understand Puppet as a response to drift and inconsistency, its features stop feeling like abstract jargon and start feeling like solutions to real operational pain. A key concept in Puppet is that it is primarily about declaring what you want the system to look like rather than spelling out every step you would take manually. That desired state approach matters because it changes how you think about reliability, since the same definition can be applied today, tomorrow, and next month, and the result should be the same stable configuration. Instead of hoping a one-time setup went perfectly, you gain the ability to reassert the baseline whenever you need to, which is especially useful after troubleshooting, after partial rollbacks, or after a machine is replaced. This model also supports the security principle of least surprise, because changes become traceable to definitions rather than to mysterious, undocumented edits. For a beginner, the simplest mental model is that Puppet maintains a contract with the machine, where the contract describes how services, packages, files, and settings should be arranged. When the machine deviates from the contract, Puppet brings it back into alignment, and that alignment is how organizations keep large Linux environments manageable. Puppet's building blocks begin to make sense when you understand the relationship between modules and classes, because those terms describe how configuration intent is organized and reused. A module is a packaged collection of configuration logic that typically targets a particular purpose, such as managing a web server, enforcing user account standards, or applying baseline security settings. Within a module, classes are a way to group related resources and behaviors so that you can apply them together as a coherent unit. A class is not a random label because it defines a named set of configuration declarations that can be included on a node to produce a predictable result. Beginners often confuse class with a programming class, but in this context it is more helpful to think of a class as a reusable policy bundle that describes how part of a system should be configured. This organization matters because real environments need shared patterns, and shared patterns reduce the chance that every administrator reinvents the same configuration differently. On an exam, questions about modules and classes are often really questions about reuse, maintainability, and consistency. To deepen that picture, it helps to understand why Puppet emphasizes modular design instead of one giant file that defines everything. When a configuration grows, it becomes difficult to review and risky to modify if all logic is in one place, because a small change can have unintended consequences across many systems. Modules create boundaries that let teams treat configuration as a set of well-scoped components, which can be versioned, tested, and updated independently. Classes inside those modules allow you to assemble those components into role-based definitions, so a database server can include a database class, a monitoring class, a baseline security class, and a logging class without duplicating logic. This assembly approach is important in real operations because servers rarely perform only one function, and you need a clean way to compose responsibilities. It is also important for security because baseline controls can be applied everywhere, while specialized controls apply only where needed, which reduces both gaps and unnecessary restrictions. When the exam uses language like reusable configuration components, think modules and classes, and think about how those components help reduce drift and make audits easier. Facts are another exam-visible concept in Puppet, and they address a problem that beginners only notice after they manage more than one Linux distribution or more than one system type. Not every machine has the same operating system family, the same network interface names, the same file system layout, or the same hardware characteristics, and automation that assumes uniformity tends to break or behave unpredictably. Facts are pieces of system information collected from a node, such as operating system details, network addresses, memory size, and other properties that Puppet can use to make smarter decisions. The point of facts is not trivia, it is adaptability, because the same class can apply a correct configuration across different nodes by choosing values based on what is true about each node. This reduces brittle branching in the human mind and places the adaptation logic in the configuration definitions where it can be reviewed. On Linux Plus, the expected understanding is that facts are used to drive conditional configuration and ensure that automation can be portable across systems without losing correctness. Facts also connect to security thinking because they influence how you minimize exposure while still maintaining functionality. If a configuration definition can detect the environment, it can apply stricter rules in one context and more permissive rules in another, based on the actual risk boundary. For example, a machine that is internet-facing may need a stricter service surface than a machine used only internally, and facts can help automation apply the appropriate posture consistently. Facts can also help ensure that a configuration is not applied incorrectly, such as attempting to manage a service that does not exist on that distribution, which could lead to confused troubleshooting and risky quick fixes. The main misunderstanding beginners have is assuming facts are only for convenience, when the more important value is reducing error. When automation is wrong, it can create outages quickly, and when automation is wrong in a security direction, it can expose services unintentionally or disable protections unintentionally. Facts act like guardrails by giving the configuration a way to confirm what kind of system it is shaping, which reduces both operational failures and accidental exposure. Now we can address certificates. Because Puppet's architecture often relies on a trust relationship between a central controller and the nodes it manages, and certificates are how that trust is established and maintained at scale. In an agent-based model, managed nodes typically run a Puppet agent process that communicates with a Puppet server to retrieve configuration catalogs and report results. If that communication is not authenticated, an attacker could impersonate the server and feed malicious configuration to nodes, or impersonate a node and inject false reports. Certificates provide a way to establish identity and encryption for this management channel using public key infrastructure, PKI, concepts. The beginner-friendly way to think about it is that certificates allow the node and the server to prove who they are to each other and protect the data they exchange so it cannot be tampered with easily in transit. This matters because configuration management is powerful, and a compromised management channel can become a single point of failure for an entire environment. The exam emphasis is typically on recognizing that Puppet commonly uses certificates for mutual trust, not on memorizing certificate command steps. Certificates also introduce a lifecycle responsibility, which means you must consider issuance, approval, rotation, and revocation in a way that supports both security and operations. If a node certificate is not trusted, the node should not be allowed to receive or apply configuration, because that would allow unknown systems to join the managed fleet. If a certificate is compromised, you want a way to invalidate it so an attacker cannot continue using that identity. If certificates expire unexpectedly, nodes can lose management connectivity, and then drift can return because they no longer receive enforcement. The reason this matters at Linux Plus Depth is that it ties together several themes you have already learned, including secure communication, identity, and the importance of repeatable baselines. A common beginner misunderstanding is treating certificates as a one-time setup detail rather than as a living part of system security. In reality, certificate-based trust is like a long-term access badge, and you must manage it so that access remains both secure and reliable as machines come and go over time. The agent-based nature of Puppet is one of the most testable contrasts, especially when you compare it to tools that are commonly described as agentless. In an agent-based model, the managed node has a resident component that regularly checks in, retrieves desired state, applies changes, and reports back, which creates a continuous enforcement loop. This can be operationally powerful because systems stay aligned without waiting for an administrator to trigger a run manually, and reporting can be centralized and consistent. It also changes your security posture because every managed node runs an additional piece of software that must be secured, patched, and monitored, and the communication channel must be protected with strong identity controls. By contrast, an agentless approach usually connects to nodes on demand, performs tasks, and disconnects, which reduces host footprint but shifts the responsibility towards securing remote access credentials and ensuring connectivity at execution time. The exam is not asking you to declare one model universally better, but it is testing whether you understand the trade-offs and can recognize which model is being described. If a question emphasizes a resident service that enforces configuration continuously, you should think agent-based, and Puppet is often used as the reference example. The difference between agent and agentless management becomes even clearer when you think about how each approach handles timing and drift. In an agent-based approach, drift is often corrected automatically on a schedule, which reduces the window during which a system is out of compliance with the baseline. That is valuable when compliance and security posture matter, because a machine that drifts into an unsafe state can be pulled back quickly without waiting for a human to notice. In an agentless approach, drift can persist until the next time automation runs, which may be fine in some environments but can be riskier in others if changes happen frequently. On the other hand, agentless approaches can reduce the attack surface on each node by removing a constantly running management agent, which can be attractive in high-sensitivity environments. The key is to understand that both models require trust, because automation needs authority to change systems, and the security question is how that authority is controlled and audited. On Linux Plus, you want to be able to articulate that Puppet's traditional model includes an agent that applies configuration and reports results, and that certificates help secure the relationship between that agent and the server. At an exam depth, Puppet's classes and modules also connect to the idea of roles and profiles, even if those exact words are not always used in questions. The underlying concept is that you can define reusable building blocks, then assemble them so that a node receives the configuration appropriate to its job. This assembly helps prevent the common mistake of applying a web server configuration to a database machine or applying development-only settings to a production system. It also helps teams standardize security controls because baseline hardening can be made a shared component that every system includes, while specialized exceptions remain deliberate and limited. Beginners sometimes think automation is about making everything identical, but realistic automation is about making systems consistently aligned with their intended roles, which can still include differences where differences are justified. Puppet's class structure supports that role alignment by giving you a named, composable way to express intent. When you see exam questions describing reusable role-based definitions and consistent application across nodes, you can map that to modules that contain classes that represent those roles. Troubleshooting and reasoning about Puppet at a conceptual level works best when you connect symptoms back to these core parts, because most failures fall into predictable categories. If a node is not receiving the right configuration, The issue might be classification, meaning the node is not associated with the correct classes or modules for its role. If configuration applies but behaves unexpectedly, the issue might be facts, meaning the node's reported properties caused conditional logic to select the wrong values or paths. If the node cannot communicate with the controller, the issue might be trust, meaning certificates are missing, invalid, expired, or not approved, and the system is refusing communication as a safety measure. If changes are not persistent, the issue might be drift and enforcement timing, where local changes are being overwritten by desired state, which is actually a feature when you understand it. Beginners sometimes interpret the enforcement loop as the system fighting them, but the correct interpretation is that the baseline is being reasserted, and if the baseline is wrong, you should update the definition rather than fighting the enforcement. This troubleshooting mindset is valuable on the exam because scenario questions often describe symptoms without naming Puppet features directly. Security implications are worth stating plainly, because Puppet is powerful enough that it can be a control plane for an entire Linux fleet, and control planes require careful governance. If an attacker gains control over Puppet definitions or over the server that distributes catalogs, they can push changes widely and quickly, potentially installing backdoors, weakening access controls, or disabling logging across many machines. That is why teams restrict who can modify configuration definitions, require reviews, and keep strong separation between development environments and production environments for automation content. It is also why the certificate trust model matters, because it prevents unauthorized nodes from joining and prevents unauthorized servers from distributing configuration. The central lesson is that automation is a force multiplier, and force multipliers amplify both good discipline and bad discipline. For Linux Plus learners, the exam often signals this by describing the need for centralized, consistent configuration while also emphasizing secure authentication between controller and managed nodes. If you can explain why certificate-based trust is critical for configuration management, you are thinking like a defender, not just a tool user. By now, the concepts should form one coherent picture that you can carry into both exam questions and real-world reasoning. Puppet fits inside configuration management, CM, as a tool that expresses desired state and then enforces it across managed nodes to reduce drift and improve consistency. Modules provide packaged, reusable configuration components, and classes inside those modules define coherent sets of resources that can be applied to nodes based on their roles. Facts provide system-specific information that allows those classes to adapt safely across distributions and environments without becoming brittle or error-prone. Certificates rely on public key infrastructure, PKI, ideas to establish mutual trust between Puppet agents and the Puppet server so that configuration distribution and reporting are authenticated and protected. The agent-based model emphasizes continuous enforcement and reporting, while the agentless model emphasizes on-demand execution with a different set of operational and security trade-offs. When you can explain these relationships in plain language, you will recognize what the Linux Plus exam is describing even when the question is written as a scenario rather than a definition, and you will be able to choose answers that reflect stable, defensible system management.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.